All right, good morning, everybody. It's about 9:20. Your lab's supposed to start in about 10 minutes, and I'm going in for surgery in about 2 hours. So I thought, hey, I can't have any food or drink, and I'm feeling a little dehydrated. Why not talk for an hour? No, I'll be good. I'll be good. But if my voice gets a little gravelly, that's why. Okay, so I want to talk about problem 3.2. Now, this problem, if you are a math or physics major, is still going to be challenging. Not because the math is outside of your control, but just because there are a lot of steps that maybe aren't clear to you as to why you should be doing them. If you've never done differential equations, what I'm about to do might seem just bonkers. But I really want you to see it. I think we can do hard things. And, well, at what stage in your life do you get introduced to hard stuff? So let's go ahead and get started and see where we go. All right, so we were asked to improve the estimates for protein synthesis rates of E. coli during a cell cycle from section 3.1 to 3.23 by including the effects of protein degradation. All right, so we've already seen this, at least some of this idea. This is the rate of change of proteins, right? If this leads to a positive result, we are gaining proteins. If this is a negative result, we are losing proteins, right? This is just a normal everyday derivative from calculus 1, okay? And we are given, this equation as an idea to get started, right? So where is this? This says that the rate of change is based off of some number that, or some function that some constant that we're going to take to be the synthesis rate, V. So this is not dependent on the number of proteins, right? And hopefully that makes sense. Why isn't the rate of change of proteins not dependent on the number of proteins? Well, proteins aren't reproducing themselves, right? If I have 5 proteins, I don't get 10 proteins faster, right? The number of proteins I have doesn't affect how quickly those proteins are made. Okay. And then this is the degradation rate, and we see that by that negative sign here, right? And the degradation rate does depend on the number of proteins that I have, right? If I'm losing, 1 protein a second, right, that would be dPdt, and I'm losing 1 protein per second because there's a rate of degradation K times the number of proteins. So if I've got 100 proteins, I'm going to be losing them at a faster rate than I would have if I only had 10 proteins, right? So that's what K is. So the units of K are 1 over time, not proteins per time. This whole thing is proteins per time. So we're asked to solve this equation. Well, if I just took you back to algebra and I said, hey, find P, you would take everything that had a P and put it on that side, and everything that didn't have a P and put it on the other side. We're going to do the same thing, but in a slightly scarier looking form. So what we're going to do is we're going to take all the P dependence here and put it to the other side. And we're going to do something that looks like a no-no. We're going to take a derivative and we're going to do what's called separate it. And then we're going to take the dt part and put it on the other side of the equation. And it looks like we treated dt as a fraction. And we're taught in calculus you can't do that. Well, the truth is you can't do that. However, there's always a way to use the chain rule to make something like this happen. So the truth is we've applied the chain rule, but physicists, we just say we separate it. Okay, and that's our method. And so I'm going to do a little bit of manipulation here. I'm going to take all of this stuff and divide it to the other side. Whereas you might have just thought, well, add that to the other side. The reason we're dividing by everything here is because we want to separate the dp and the dt dependence. And if I multiply dt and I have, some terms over here and some terms over here, that's going to mix it up. So this is the only way that I can get the dp and the dt terms in a separated way. So it looks kind of messy, but it still works. Now I'm going to do a little bit more manipulation here because I know where I'm going for the answer. You might just start here and your math might look very different from mine, just because I played with it a little bit more. Okay, and so what I'm doing here is I'm just factoring out a minus sign so that I don't have a minus sign in front of my p. And then I'm taking this k and I'm factoring it out of the denominator partially. I can't take it out all the way, and I'm putting it over here. Why am I doing that? Well, because I know that I'm going to get an exponential, and I know that that exponential is going to depend somewhat on k. So I'm building this exponential as we get started. If you're looking at this going, why would I do any of these steps? That's fine. Don't worry about it. I'm not asking, hey, could you do this from the start without any help? I'm saying, now that you've got a solution, can you do this problem? And I think the answer is yes. So we're going to cross multiply stuff, and I don't like negative signs over here, so I'm going to put them over here. And so this is now the equation that we have. We've got dp over p minus v over k, and both of v over k are just constants. These are talking about my synthesis rate and my degradation rate. And then I have a minus k dt here. And so now I'm just going to go back to Calc 1, and I'm going to integrate this thing. And this side is pretty easy to integrate. That's just a constant times dt. But this side's a little messier looking, and you may not recognize that integral right away. But I promise that if you did Calc 1 and you did any integrals, you did see this. At k, it might have been the start of Calc 2. I don't know our sequence as well. But generally, this is like the end of a Calc 1 course. But if not, don't worry about it. We're going to do it. Okay. So I've got that integral to do, and what we often do is called a u to u substitution, and that's just a convenience. We're saying we're going to, instead of integrating this ugly thing, we're going to use a substitution to make it less ugly. And so we're going to take this whole denominator, because it looks scary, and we're going to call it u. That's it. And then if I take the derivative of this, with respect to p, well, all this constant stuff goes away, so du is just dp, right? Hopefully that makes sense. And now we're setting up our integral of du over u. And then this thing was a constant, so we brought it out front. So we've got minus k dt. And when you integrate du over u, that leads with the natural log. And when I integrate dt, I just get t. And then you always remember we get a plus constant because I didn't set these limits here on my integration. So our solution is then natural log of u minus kt plus c, in which we're good to go, except no one likes logs, right? That's why we burn them. So what we're going to do now is exponentiate this whole thing to get an equation that looks more like something that we want. So we plug back in what our answer for u was, we exponentiate each side, and we're left now with something that looks like this, right? We just undid the natural log here. On this side here, we've got e to the c and e to the minus kt. Well, what is c? C is just a constant. What is e? E is just a number. E is 2.718, and it goes on forever just like pi. So e raised to a constant is still just a constant. So physicists love to just say, well, it's now my new c, right? So just so we're clear, this c is not the same as that c, but we don't care because all we know is we have a constant. All right? Some people, prefer to call this like c prime because they want to keep track of it. I don't like the extra terms. It's a constant. That's all I care about. Okay, so I now have a formula that I'm building. And just so we're clear here, this is p as a function of t, right? That is, let me just actually change that a little bit and say that's p as a function of t, right? This is the number of proteins as a function of t. This is the thing I'm looking at to try to make a better estimate. And so we just do a little bit of algebra now, and I solve for it, and I say, okay, there we go. That's just moving it to the other side like normal algebra. And now I want to find that constant. And so we say, okay, what values do we know that we could use to plug in? Because remember, this is no time dependence. That is no protein dependence. If we know its value at any time, we know its value at every time. All right, so what we're going to do is say, okay, at time 0, right, at p not 0, this is the initial number of proteins I had, I plug in 0 everywhere, and I get v over k plus c. That means that c is also the starting protein concentration minus the ratio of the degradation rates. This is just algebra, right? Now, do I know the starting protein concentration? That's a much easier number to know than just some random constant. So for c, I'm going to plug in this value instead. And so now we get an equation that maybe looks a little bit messy, maybe doesn't look as much fun, but it is very helpful if you know how to look at it. So we just took this term, we plugged it in here, we did a little bit of algebra, gathering up v over k terms. We distributed the exponential through each of those terms, and we're now left with this thing. Now, one thing I want to be clear about. e to the minus kt. What does that look like? Well, if we make a plot of e to the minus kt, at time equals 0, this is just e to the 0, so that's just 1. It starts at 1, and then it decays forever. Why is that? Hopefully we all understand what we're reading here. But e to the minus kt, right, is just 1 over e to the kt. And we know that e to the kt is one of the fastest growing functions we know about. So over a long period of time, this thing drops to 0. So if we look here at my proteins as a function of time, and we say let time run, this is going to get really small, right? This is going to get really small. And what we're going to find is after a long period of time, this is our stable number of proteins, right? So that's our concentration of proteins after a long period of time, okay? But let's look a little bit closer. What are these other terms? Well, this term right here says I have some number of initial proteins, and those proteins are falling apart, right? What is that? That's our decay term. That's how our initial concentration of proteins are falling apart. Well, what's this term? V over K is the rate at which I'm making new proteins. But then some of those new proteins themselves are also decaying. But because those new proteins don't themselves make more proteins, we don't have to worry about them making new ones. So this is the degradation rate of the proteins I start with. This is the synthesis of new proteins, and this is the degradation of the synthesis of those new proteins. And what does that function look like? It looks something like this. It itself will also tend to a stable value of roughly v over k, right? Something like that. That tells me how many proteins I have after a long period of time of degradation. Okay, so we now know how many proteins I have as a function of time with degradation happening. Let's now use it to make better estimates, or at least set ourselves up to make better estimates. We are told in the problem that we have a half-life of these proteins, which is about 60 minutes, which is about 3,600 seconds, right? Half-life just means at 3,600 seconds, you have half of what you started with. So, our goal, let's just back up for a minute. Our goal is to find values for V and K that can improve our estimates, right? What is the synthesis rate? What is the degradation rate? So we know the half-life of the protein is about 60 minutes, or about 3,600 seconds, right? And we know decay looks something like this, right? I have some number of proteins. What's the rate of change of proteins per time? It's based on how many I have times the rate that they're doing. This minus sign tells me that I'm getting smaller, right? And so we know the solution to that, right, is just this. This is based off stuff we've already done in class. It's just exponential decay. Now, at 1 decay time, or 1 tau, we should have half of our proteins. This is 1 half-life, right? We should have half of the proteins we started with. So we can just plug that tau in, and we now say, okay, I'm going to get half at 1 tau, which is equivalent to plugging in tau on the other side. And I can now solve for K. And so I now get, right, this equation here because the p naughts went away. I then keep doing algebraic manipulation, and I'm left with K equaling this right here, right? This is just algebra. If you're watching this and going, oh my God, this is way too fast, slow down, I can't take notes, I understand. I am talking fast because I wrote it all out ahead of time because I wanted to make sure it was really clear. And for some reason, I thought if you watched me write the math, that wouldn't be as enjoyable. But this video is on YouTube, so you can pause it. You can back it up. You can go at whatever rate you need to go. You are watching this with your peers to try to get some help from them. But at the end of the day, when you go home and you do your own problem, you've got it at your own leisure, okay? And what does it mean to do your own problem if you have the solution? Well, what I mean is when you write up that solution, I want you to literally do that. You've got a ton of check steps. But the goal is for you to write out your solution. Take this, make it your own, right? You could copy mine, but that's boring. What a waste of time, right? Education isn't copying what someone's done. It's learning from what someone's done. So yeah, you've got checkpoints. Go home and use them. So this is K. Let's assume you sat down, you worked through it, you see where it comes from. Oh, got it. Maybe I would have done it myself, but I got it. And now we can, do a little bit more manipulation here and say, well, our log rules, right? When I have log of A over B, that's log of A minus log of B. So we're going to do that, and we're going to do that specifically because log of 1 is 0. So we now work this out, and we get log of 2 over tau, and tau is 3,600 seconds. We can plug that in, and we get something like 2 times 10 to the minus 4 seconds. So we now have a better estimate for our degradation rate. Excellent. Now, what about the doubling time? Well, the doubling time was told us to be about 3,000 seconds, which I'm going to cheat and say that's about 3,600 seconds. Maybe you don't like my number. That's fine. Use your own number. It will still work. And so we go back to our equation for how many proteins we have as a function of time. And we're now going to plug in tau here. And when I plug in tau there, this is now my doubling time. Roughly how long does it take to get twice as many proteins as I started with? So I plug in my tau, and that's my goal, is to get twice as many as I started with. So I'm literally just solving this equation. And so we have this ugly looking thing. I'm not going to lie, it's pretty ugly, but my goal is to find V. So this is just an algebra game now, right? I'm taking this whole term, I'm dividing it over there. I'm taking that K, I'm putting it over there. And now I'm just plugging in numbers, right? It's messy, but it works. And when I plug in numbers, I get about 2,000 proteins per second. And so now I've got my degradation rate, I've got my decay rate, and we can do a better job. I think there's still a couple of questions left to be answered in this problem, but this is the math behind it. This is what it means to do differential equations and solve problems. I personally think this is really exciting, and I hope that you at least appreciated it for what it is. Hopefully I'll see you guys next Friday over Teams. Hey, thanks a lot. Goodbye for now.